Specific heat is what we're going to talk about today for this video. And specific heat is a property of all matter. So every substance has a specific heat. The specific heat changes if it's a solid, a liquid, or a gas, depending on its phase. But let's talk about what it means. So this is a measurement or a property that determines how much energy is needed to change the temperature of a substance. So for example, if you have water has a pretty high specific heat. It takes a lot of energy to change its temperature. We all know this because if we try to boil water, it takes forever. It takes a lot of time. It takes a lot of energy and heat to boil the water. Um, Something like aluminum metal has a much lower specific heat. And the reason that I kind of know that is I know if I put aluminum foil in an oven, like I'm cooking something, and I take it out, I can kind of touch it pretty quickly. It doesn't take very long for it to cool off. So it loses and gains heat and changes its temperature pretty rapidly without a lot of time or energy. Other materials are different, and that's like a trait of them. So the way that we measure specific heat is in joules per gram degree Celsius. So what this means is that specific heat is how many joules does it take to raise 1 gram of a substance 1 degree Celsius? Or how many joules of heat are released when 1 gram of a substance loses or the temperature reduces by 1 degree Celsius. So that's kind of what that means. And this is the formula that we use when we are dealing with this type of situation. So Q is your energy or heat, which we measure in joules. M is mass, measured in grams. And delta T, so the delta, that's what that little triangle means. Delta means change. It's a mathematical term. So if you delta T is a variable in itself, and that's the change in the temperature, which is always the final minus the initial temperature. So what we can do with this is we can calculate how much heat is needed to change the temperature of different substances. And we can also use it to calculate mass or change in temperature or specific heat. So we have, let's see, was it 1, 2, we have 4 variables here that we can play with. Technically 5 if you think of temperature final and temperature initial. So let's go through a couple of examples and then I'll show you the packet. Okay. So in this case, we have a 500 gram cube of lead is heated from 25 degrees Celsius to 75 degrees Celsius. How much energy was required to heat the lead? The specific heat of the lead is, excuse me, 0.129 grams per joules degree Celsius. So what we need to do here is let's highlight all the information and what we're trying to figure out. So it looks like we're trying to solve for how much energy. So it's going to take energy to heat any substance up. Energy, of course, is in joules. Looks like we have 500 grams, which we know is mass. And it looks like we have the temperature. Okay. So it was heated from 25 degrees Celsius to 75. So this is the initial temperature, Ti, and this one is Tf, which is the final temperature. And we also have the specific heat. So with any problem like this, it's really good. We have a formula that we can use. So let's go look at the formula and we're going to write it down. Now, big question, do we need to rearrange this formula at all? Is the variable we want isolated? The answer this time is it is isolated because we're looking for Q, which is energy. That's just the letter we use for it. I don't know why, it just is. So we're good to go. So we just need to plug in all our variables. Our mass is 500 grams. Our C stands for specific heat. Why does C stand for specific heat? I don't know, it just does. I think it means for capacity or something. I don't know. It's a whole thing. Don't worry about it. It just is. So let's multiply that by 0.129 joules per gram degree Celsius. And then finally, our delta T, which is our change in heat. So I like to kind of pull this aside like a little, like a little, put some brackets or parentheses there. The delta T is always final minus initial. So our final temperature was 75 degrees Celsius and our initial is 25 degrees Celsius. So we have to kind of do that math first. If we do that, that of course is 50 degrees Celsius. Okay. And then looking at our units here, we're looking for joules. It looks like grams and degrees Celsius will both cancel out and we're just left with joules. So that's very good. And now we'll just plug in the numbers. So it looks like 500 times 0.129 times 50. And that's going to equal 3,225 joules. Seems good to me. Seems like a reasonable number. Yeah, if it takes, it doesn't quite take a whole joule to raise it 1 degree Celsius, but we've got 500 grams. That's a lot. So yeah, we're already getting up there, and we do have to raise it 50 degrees Celsius. So that seems like a reasonable number to me. Okay. And that's pretty much how you solve it. So that's what this means. That's how much energy we'd have to input. Whether we are putting that maybe on a stove or wouldn't put it in a microwave, that wouldn't work very well. However we want to do that, we have to somehow add that amount of energy. Maybe we're putting this in hot water. Maybe we've got water that's at 75 degrees Celsius. We just put it like in a water bath. That's hot. 75 degrees Celsius is, what would that be? I don't know. It's probably like 200 degrees Fahrenheit or something like that. Something, maybe not quite that hot, like 175. I don't know. You could put it in an oven. Something like that. Anyway, we're adding heat. We're adding energy. Okay, let's try another one. A 25-gram metal ball, so that's information, is heated 200 degrees Celsius with 2,330 joules of energy. What is the specific heat? Okay, so for this one, we have been given, the mass. Now this one says is heated 200 degrees Celsius. That is the temperature change. We don't know what the final was. We don't know what the initial was. We just know it went from one temperature to another temperature and it gained this, the temperature went up 200 degrees Celsius. So this actually is our delta T. So this is grams. This here is our delta T. Sometimes you just get the delta T, sometimes you have to calculate it. So this one's a little easy, that's nice. We've got our energy, which is in joules, so that's cool. And we need to calculate our specific heat. Specific heat is C. That's the symbol for it, and it's always measured in joules per gram degree Celsius. So that's kind of what we're looking for. So let's start with our formula. All right, we need to solve for C. So our formula as it is right now is not isolated. We have not isolated the correct variable. So let's go ahead and do that. Let's just divide both sides by m delta T. So we're going to have C is equal to Q divided by m delta T. And we'll just plug in our variables. So 2,330 joules divided by 25 grams times 200 degrees Celsius. And that is going to equal 2,330. Yep. Let's see if I can do the math correctly. Divided by 25. I like to just hit and divide it again. That's just my personal preference. Okay, so it looks like 0.466 joules per gram degree Celsius. All of those units have to be included. Okay. And you know what? Metal tends to be less than a joule per gram degree Celsius. That's pretty normal for metal, so I would believe that number. Seems reasonable. Okay, so that is how you do these kinds of problems. It's just a different kind of algebra problem, just knowing what all the pieces and parts are. So let's take a quick look at our unit packet. For specific heat, it looks like we have pages 9 and 10 and 11 and 12 and 13. Yeah, 13 is where it stops. Now, some of these problems are calorimetry, but let's just start with an example or two. Let me just pick out one that I like. Calculate the specific heats. 20 grams. Yeah, okay. Let's just do let's go run through maybe the first couple here. I'm going to double check some of these. There's a couple problems here you might need to skip. So just be aware of that. I'll see if I can find those. So just kind of keep your eyes open. ask me if you're not sure. Okay, I'm going to leave number 1 to you. I think you can handle that. It's in your notes. You can copy it down. That's pretty easy. Let's do 2 for sure. So how many grams, that's what we're solving for, of water require 2,200 joules of heat to raise its temperature from 34 to 100 degrees Celsius, and the specific heat of water is 4.18 joules per gram degree Celsius. Okay, so let's set up our formula. Q equals MC delta T. We are solving for M, so we're going to need to divide each side by C delta T. People call this equation, by the way, they call it the MCAT equation because mass C delta T, it kind of looks like MCAT. So if you ever hear it. So we just need to plug in our variables. Q is the joules. C is the specific heat. And the temperature change, again, we started at 34 and we went to 100. So that's going to be 100 degrees Celsius minus 34 degrees Celsius. Okay, so now we just need to do that math. So I'm going to input it in my calculator this way. 2200 divided by 4.18. And I'm also going to divide it by, I'm going to put this in parentheses just for PEMDAS purposes, 100 minus 34. Okay, yeah, that looks pretty good. And I got 7.97. So 7.97 is the mass, and that's grams. Seems reasonable to me. If you go through this, you're going to find that the joules cancel, as do the degrees Celsius, and you're just left with grams as the only unit available. So you know that you've probably done the problem correctly. All right, let's do another one. It was so awkward for me because I don't have I want to wait for questions, but obviously no one's here, so I can't do that. Okay, a block of aluminum weighing 150 grams is cooled from 98. Now cooled, ooh, let's pay attention to that. From 98.4 to, my lights went out. There we go. 62.2 degrees Celsius with the release of 1,080 joules of heat. From this data, calculate the specific heat of aluminum. Okay, so that's what we're solving. So Q, MCAT. We're solving for C. There's only so many options of things you can solve for. So that would be C is equal to Q over M delta T, Q mat, I guess. The Q is the 108 joules. Now, something a little funky here. This number is actually negative. And here's why. It's because we are releasing heat in this situation. So gaining heat is positive, releasing heat is negative. And you're going to see why that's kind of important in a second. Okay, mass was 140 grams. And we have to multiply that by the change in temperature. Now, here are the changes. It is cooled. The initial temperature was actually the hotter one, and the final was the colder. So we actually have to do 62.2 degrees Celsius minus 98.4 degrees Celsius, which, if you can think about it for a second, is going to be a negative number. But if we've got a negative number in the here and we're dividing it by another negative number, it's going to work out and be a positive. So here's how I'm going to enter this. Oops, I got to get these lights back on. Hold on. 1 second. Yeah, that's much better. We'll turn this light off. The glare drives me crazy. So negative 1080 divided by 140, that's positive, divided by, this is going to be 62.2. Oops, yep, my 6 doesn't always show up on my calculator. I have to push it. Really have to mash that button. There we go. 6.2 minus 98.4. And we end up with a positive number because the two negatives cancel. So that's nice. So that's 0.21 joules per gram degree Celsius. Again, we're dealing with specific heat. Okay, so let's talk about one more concept here. Let me find a good problem to give you an example for this. This is, there's a lab that we're going to do about calorimetry. So let me see what we've got here. Oh yeah, this one's good. I'm going to go to page 11. And we are going to look at number 4. Okay. So there's this thing called calorimetry, and calorimetry is a process. The word calorimetry refers to calories, which you would probably recognize as energy, energy in food specifically. Calories are the kind of American unit for energy. Joules are the metric unit. Actually, if you go to Europe, you'll find that food packages have J's instead of CALs because they measure it in joules, but it's the same concept. So here's the kind of question we've got. We've got a sample of a metal. Here, I'm going to pull out a sample of metal. There we go. There's some copper. Okay. And we heat this up to 82.25 degrees Celsius. And we want to figure out what the heck is the specific heat of this metal. Actually, it doesn't matter if we heat it up. The idea here is, how do we figure out the specific heat? Well, we can heat this metal up. To find the specific heat, we need 3 pieces of information. We need energy, temperature, and mass. So finding the mass of this metal, that's easy. We put it on a balance. I can do that no problem. We can all do that very easy on a scale or whatever. Finding the heat, that's really hard. Measuring the temperature, again, pretty easy. We have a thermometer. Like, hey, I got this digital thermometer. That's not hard. But the heat is difficult. How do we measure that? Well, as it turns out, we can't. There's no instrument that just allows us to measure heat. But what we can do is, if we heat this metal up and we put it in colder water. So if we heat this metal up to 82.25 degrees, and then we put it in 24 degrees Celsius water, what's going to happen? Well, the water temperature is going to increase. And we know the specific heat of water. The specific heat of water is 4.18 joules per gram per degree Celsius. It was in a problem from earlier. So let me write that down. The C of water is 4.18 joules per gram degree Celsius. If we put this metal in the water's temperature is going to increase. The metal is going to cool off. And we can calculate how much, if we have the temperature of the water and the mass of the water, we can calculate how much heat the metal released into the water. That will be the same amount of energy. Yeah, the whatever energy the water gained, that was the amount of energy that the metal lost. Then we can take that energy and go back and solve for specific heat. This whole process is called calorimetry. We're going to do a whole lab where that's exactly what we do with, in fact, these copper pieces. And we do it in something called a calorimeter. And in this particular case, we just use an insulated cup. We use coffee cups. And we add water into the coffee cup. There's a hole at the top. Here, I'll show you. Let me stop this for a second. Coffee cup. There's a little hole at the top where we can put a thermometer. And we can just measure the temperature change of the water. So we're going to have to do 2 calculations to solve this. And there's a key concept, again, about the heat from the metal being absorbed by the water. So let's walk through that process. Again, we are going to do a lab. So there's a whole video that's just this, and it's a really good demo. But let me show you. Okay, so we've got 2 scenarios here. So we've got a cup that contains water. I'm going to highlight that whole thing, underline the whole thing. And it's at 24 degrees Celsius. We also have a sample of the metal, and it's at 82.25 degrees Celsius. The final temperature of both is 28.34. So that makes sense. The water temperature increased, but the metal temperature decreased. Makes perfect sense. What is the specific heat of the metal? Ooh, specifically the metal, not the water. So if we want to solve for the specific heat of the metal. So let's get two situations here. We've got water and we've got the metal. And so again, we've got a cup here with water and a chunk of metal. Okay, so the water is the 75.0 grams. The metal is 26.00 grams. And yeah, so that's kind of the scenario that we're looking at. So let's start with the water. Let's see what's going on with the water. So the water, actually, no, we'll start with the metal. The metal, we are trying to solve for C. So C is equal to Q over M delta T. So the Q is a problem. I don't know how much energy that this metal lost. It definitely lost energy. So I'm going to put a negative sign there. And it's going to be some number and it's going to be joules. But I don't know what that is yet. But maybe we'll be able to set up the rest of the problem and we can kind of figure it out. The mass we do have. And the temperature change we also have. It started off, it ended up at 28.34 degrees Celsius, and it started off at 82.25. Sorry, yeah, so that's our final and initial temperature. And if we can get the joules, we should be able to solve this problem. To get the joules, let's go back to the water. If the metal lost energy, the water must have gained that energy. So Q equals MC delta T. We're solving for Q. All right. So the mass of water is 75.0 grams. The specific heat, oh gosh, I'm going to run out of space here. That's okay. Is joules per 4.18 joules per gram degree Celsius. And then the temperature change, I'll have to put it down here. The water ended up at 28.34, but it started at 24. Okay, so we're going to solve for this. So Q for the water is going to be equal to, let's see, that's 75 times 4.184. Whoops, 4.184. Oh no, 18, sorry. Times that temperature change thing. So that's going to be 28.34 minus 24.01. No, is it just 20? No, just 24. And it looks like we've got 1,360.59 joules. Okay, and that's a positive number. That's how much water energy the water gained. So what we're going to do is we're going to take that number. We're going to take it all the way over here and put it in here. Because that's the amount of water, that's the amount of that energy came from the metal. So therefore, that must be the correct amount. I'm just going to erase that joule here and put it at the end. 1360.59 joules, but it's a negative sign. Now we have all the information that we need to solve this. We have the heat, we've got the mass, and we have the temperature change. So let's take that. I'm going to take that number and multiply it by -1. And I'm going to divide it by 26. I'm also going to divide, 26, because again, that 6 does not work on this calculator. Divided by 28.34 minus 82.25. Okay, and the answer is, so the C for the metal is going to be 0.97. Oh, God, you guys can't read that at all, can you? We'll put it up here. 0.97 joules per gram degree Celsius is equal to the C of the metal. So that's the answer. Okay. Which seems reasonable to me. Metals being around 0.97 seems pretty reasonable. Water is way higher. Metals tend to be less than 1, so that's about right. So that's a calorimetry problem. So if you see problem number 5, that's going to be very, very similar. Let me see. We've got any others. Yeah, that one's pretty good. The next page, page 12, and 12 and 13 are a lot of that kind of problem. I think there's a couple. Oh, like here, number 12 is one. Yeah, 12 is similar. Yeah, some of these are a little funky, but anyway, I'm going to go over those. So that's all of those problems that at this point, I think you can kind of handle. Let me just double check something here. Oops, I just dropped my calorimeter. Just while I'm here, let me just take a quick look. Oh, actually, specifically page 20, that's the other one. So page 20 is all calorimetry practice. And that's the last page that you guys will probably have to work on. So, all right, that's pretty much it for now. Thanks, y'all. Hope that was helpful.